Chapter 6 is all about factoring polynomials. Basically undoing multiplication, coming up with what are the factors, what are the expressions that you would multiply together to get your result. So in order to perform factoring, we'll learn how to find the greatest common factor of a list of integers, and then how to find the greatest common factor from a list of terms. And then we'll practice factoring out the GCF, greatest common factor from a polynomial, and then start with factoring a polynomial by grouping. So, it's very important that you know how to factor out a greatest common factor, GCF. Greatest is important, common is important when we're describing the factor, the greatest common factor. So if I wanted to know the greatest common factor of the numbers 45 and 75, I want the biggest, the largest, the greatest number that can be divided evenly into both 45 and 75. And the process for finding the GCF is come up with a factor tree. So pick any two numbers multiplied together that will give you 45. And so we have 5 times 9. Now since 5 is a prime, the only factors are 1 in itself, we're going to circle it. But 9 is not a prime. 9 can be written as 3 times 3. So all the nodes have circles on them now. So 45 is 5 times 3 times 3. We're going to do the same for 75. So I'm going to say that that's 3 times 25 is 75, and 3 is a prime number. And 25 is 5 times 5. And our 5s are numbers. So on the side, now I'm going to rewrite 45 as its list of prime factors. 3 squared times 5. 3 times 3 is 3 squared times 5. And underneath it, I'm going to write 75 as a list of its prime factors. So we want any factor that is common to both. Like see here I have a 3 and a 3 squared. 3 is common. And this is 3 to the first and this is 3 to the second. So the largest exponent that is included in both numbers would be 3 to the first, because there isn't a 3 to the second in 75. And you know what? 5 is also common to both 45 and 75, but the largest one that's included in both is just 5 to the first. So then we multiply these. 3 times 5 is 15. 15 is the biggest number that can go evenly into 45 and 75. We would call that the greatest common factor. All right, so let's do the same operation for 32 and 33. Let's write the list of prime factors. So 32 is going to be 2 times 16. You could have picked 8 times 4. 2 is a prime, but 16 is not. And I'll say 16 is 4 times 4. Neither one of those are prime. 4 is 2 times 2. And this 4 is also 2 times 2. And now we have 33. 33 is just 3 times 11. Those are the two prime factors of 33. So on the side, 32 is 2 to the 1, 2, 3, 4, 5. 2 multiplied by itself 5 times. 33 is 3 times 11. So now we want to find any common factors. This has a 2, no 2's in 33, no 3's in 32 or 11. So the only number that can go evenly into both 32 and 33 is the number 1. There are no other factors that go evenly into both numbers. Okay, and here we want to find the GCF of 3 numbers. 14 is 2 times 7. 24 is going to be, I'm going to pick 2 times 12, but the 12 is not a prime. So I'll say that that's 3 times 4. But the 3 is prime, but the 4 isn't. And then my 4 broken into primes is 2 times 2. And then the number 60. 60 as prime factors would be 5 times 12. So you could have picked 6 times 10 or any other two numbers multiplied together that give you 60. And 12 is going to be 3 times 4. And 4 is 2 times 2. So on the side, 14 is 2 times 7. 24 is 2 to the third times 3. And 60 is 2 squared times 3 times 5. And we want the greatest common factor. All right, well here 2 is common to all three of my numbers, but here's 2 to the first, 2 to the third, and 2 squared. So 2 to the first is the largest 2 to the first is the largest exponent 2 can be raised to in all three numbers. 7 is not common in all my numbers. 3 is not common in 14, 24, and 60, and neither is 5. So the GCF, the largest number that goes evenly into 14, 24, and 60, is 2. So you're going to try practice 1C. For classroom example 2, now how do you find the greatest common factor from a list of terms, variables raised to exponents? They have to have the exact same base, and then it is always the lowest exponent. So here I have y to the fourth, y to the fifth, and y to the eighth. The GCF of those three would be y to the fourth. The GCF of x and x to the 10th, this is x to the first, x to the 10th, would be x to the first, or we would just probably just say x. X is the GCF of these two terms. It's always the lowest exponent. Okay, so you're going to try practice 2. And so now we've found how to find the GCF of numbers and also how to find the GCF of variables raised to powers. Now it's time to find the GCF of a list of terms. What if I wanted the GCF for negative 9x squared, 15x to the fourth, and 6x? Well, let's try negative 9. That'll be negative 1 times 9. And 9 is 3 times 3. 15 is 3 times 5. Now before I go to 6, as I look here, I can tell that 3 is going to be my GCF so far. All right, so you don't really have to fully factor all the numbers. If you can tell that you're limiting down the common factors, you can kind of tell what you're looking for here. But so 6 is going to be 2 times 3. So negative 9 is negative 1 times 3 squared. 15 is 3 times 5. And 6 is 2 times 3. Well, -1 is not common to all, but here I have my 3's are factors in all of my numbers. And 5 is not in all the numbers, and 2 is not in all the numbers. So my GCF, the numbers, the coefficient part would be a 3. Now let's look at the variables. The GCF of x squared, x to the 4th, and x is going to be x to the smallest power. Or we'd probably just make that 3x. So you find the largest GCF of the numerical coefficients, and then you find the largest GCF of the variables. Okay, so how about if we wanted to find the GCF of 11ab to the 3rd, a squared b to the 3rd, and ab squared? Well, 11 is, it's actually prime. 11 times 1. And then 1 is a prime, and 1 is a prime. So as far as the coefficients go, 1 is the GCF. Now let's look at the a's. Here I have a to the 1st, here I have a squared, and here I have a to the 1st. All three terms do have an a in it, but the lowest degree would be a to the 1st. And now let's move along to the b's. We have a b to the 3rd, we have a b to the 3rd, and we have a b squared. B is common to all three of my terms, but the lowest degree is b squared. So actually ab squared is the GCF of 11ab to the 3rd, a squared b to the 3rd, and ab squared. So that's how you find a GCF. Now, what are we going to do with a GCF? This is basically undoing the distributive property. We want to factor out the GCF. That's our phrase. We're going to factor out the GCF. In other words, we're going to pull out a GCF, and we're actually putting in parens in our examples. So what's the GCF of 49 and 35? Well, 49 is 7 times 7, and 35 is 5 times 7. So the GCF of the numbers, the coefficients, is going to be 7. Now how about the variables? This has an x to the 1st, and this doesn't even have an x. So x is not common. So never mind being greatest, it's not even common to both terms, which means my GCF for these two terms is 7. So I'm going to factor out the 7. What is 49x divided by 7? Is 7x. Bring down your minus. What is 35 divided by 7? It's 5. So I have just factored 49x minus 35. And whenever I factor, I always check my work. I always quickly go, what is 7 times 7x? 49x. What is 7 times -5? -35. Is that what I originally started with? Yes, it is. So it checks. So once we find the GCF, we factor that out, we pull that out and put in parens. So here I have z to the 3rd and z squared. Well, they both have a z, so the GCF is going to be z squared to the lowest exponent. So what is z to the 3rd divided by z squared? That's z. Bring your minus. What is z squared divided by z squared? Any number over itself is 1. So I factored out my GCF, I factored out my z squared. And again, I always check. Z to the second times z to the first is z to the third. Z squared times -1 is z squared. Is that what I started with? Yes, it is. So it checks. So that's the first few examples of us factoring out a GCF.